what would be fun to do would be to show the trajectory of the bird. And so this is kind of the tricky part of this activity that a lot of students have trouble with. And there's a couple of things that can go wrong here. But the first thing we should do is just go ahead and stick this into the code. And you want to put this in the code somewhere after the display function. So there's the display functions down here. If you put it before the display function, you won't see anything, unfortunately, because the display function clears the whole screen. But if I click the button, I'm going to do Control V to paste that thing in there. Computer does not like the question marks. All right, let's talk about this for a second. So I want to switch over for a second. So whenever you have something that's sort of flying through the air, right, there's a particular equation that describes it. Now, where these equations come from, if we had more time, I'd be happy to show you. But if you remember from the Apollo moon landing activity, which hopefully you just did, the y value as a function of time is equal to the initial y value, so y0, let's call it, plus vy0. I think in our code it's called v0y, so let me do that. v0y, and then times the time, plus 1/2 gt squared. Okay? So if you remember from Apollo moon landing, we had the ship starting from rest, and so we were ignoring this term. We still had this term, and we had to calculate how many seconds it was falling, things like that. So this should be slightly familiar to you. We didn't talk about what happens to the x variable for something that's just falling to the ground. So for the Apollo moon landing, if there wasn't any initial velocity in x, you just sort of kept with the same x value. So that wasn't very interesting. But if you did have an initial velocity in the x direction, your x position as a function of time would look something like this. So x0 plus v0x times the time is what you would get. And so as things move on, as things move through the air, for example, this is the equation that describes, this kind of trajectory. So something like if this is x and this is y, it describes something like that. Okay? So here's my x. So ultimately, this is what we need to put into the code. So this is Math World, for example. But we need to put this into Computer World. There's a couple of things that we got to do for Computer World. For one is that to do Computer World, so let me cross this out, Computer World. So for one, this has to have an asterisk between it, right? So you have to have asterisks whenever you're multiplying things together, like so. The other thing you might want to bear in mind is that different programming languages treat the squared differently. So here, instead of doing, so some programming languages you can do this thing, but not in ours. So for example, MATLAB, this is fine. Desmos, this is fine. But for JavaScript and many other languages, this is not going to work. So instead, what you should do is t asterisk t. So hope you would agree that t times t is t squared. If you really wanted to, you could do t asterisk squared that way. So this is more of a Python-y way of doing it. And then finally, you could also do pow. Third way you could do it would be pow t comma 2. That would also work. For us, we're gonna do it like this in just a second. But there's some options. I can't remember if this is pow or power. But sometimes when you're squaring things, you got to think a little bit. So it's something you have to worry about in Computer World, not so much in Math World. Math World, we all know what this is, right? So those are some of the subtleties that we have to do. We also have to figure out what variables there are. So in the code, You know, we have a variable v0x, we have a variable v0y. So that part is relatively straightforward, but there is some things to think about as we go from math world to computer world.